Alright, this video is going to be on our vectors part 2, where we're going to talk about scalar multiplication, addition, subtraction, dot product, and so forth. Okay, multiplying by scalar. Notice all of these different variations. We have our vector v sitting here, and so if we multiply this vector by the scalar 2, that's going to make this twice as long. If we multiply it by 1/2, we're going to make it half as long. And then if we multiply it by a negative, we're changing the direction. We're making it go in the opposite direction. And if we're going to add vectors, notice that whenever we add them, the sum of these is called the resultant and extends from the tail of V to the tip of W. So we're going to add from tip to tail. And then the difference is still going to be the same as far as representing the difference of these. It's shown it's still tip to tail. And you're going to say V minus W, which is the same thing as V plus the opposite of W. So whenever you're looking at these in your scalar multiplication, let's say K times V, well, that's going to be, you come up here and look, here's vector V. So K times V is going to be K times A sub 1, comma, K times B sub 1. Notice A sub 1 and B sub 1, they are in component form. Okay, and then on the addition of V and W, you're just going to add the corresponding component parts. So you're going to say A sub 1 plus A sub 2, comma, B sub 1 plus B sub 2. And then on your subtraction, it's just what you think it would be. A sub 1 minus A sub 2, comma, B sub 1 minus B sub 2. Now let's look at our examples. And the first example says 2 times C. So 2 times negative 4, 5. So that's going to give you negative 8, 10. Okay, and then A plus B. So you're going to add negative 6 plus 1, comma, 2 plus 7. And so that's going to give you negative 5 and then 9. And now you're subtracting, so you're going to have C minus B, so negative 4 minus 1, comma, 5 minus 7. And so you're going to have negative 5 and negative 2. Whoops. Almost didn't write my 2. And then A minus 3 times C. So you're going to have A minus 3 times your C value, which is negative 4, comma, and again your A value, minus 3 times your C value. And so, let's see, negative 6. Uh-oh, I left off my negative. Draw the guns. Let's see, that's going to be 6, comma, negative 13. There we go. All right, now 5 is going to be 1/2 a, so you're going to multiply everything in a by half. And so you're going to have 1/2 times negative 6 minus 1. 1/2 times 2 minus 7. And so when you go through all of that, let's see, 1/2 times negative 6 is negative 3. Negative 3 minus 1 is negative 4. And then 1/2 times 2 is 1. 1 minus 7 is negative 6. And then for 6, we're going to have 4 times 1, which is going to be 4. Plus 5 times negative 6 is going to be negative 30. And then we're going to have 4 times 7, so 28, plus 5 times 2, which is 10. So we're going to have negative 26, comma, 38. All right, unit vectors. To find the unit vector, we are going to have, the unit vector is always equal to 1, but we need to find the unit vector, and the unit vector is going to be 1 over the magnitude of vector v times vector v. That's how you find the unit vector. The magnitude of the unit vector is always 1. So let's find the unit vector of some of these problems. So the first thing you're going to do with this is find the magnitude of vector v. And it's going to be the square root of 5 squared plus 12 squared, 144. And so you'll put that in your calculators, and that should give you 13. And then you come back with the unit vector. It's going to be 1 over 13 times your component form, negative 5, 12. And so the final vector is going to be negative 5 over 13, comma, 12 over 13. All right, let's look at number 8. Again, you're going to find the magnitude of n, and this is in component form, so we're just going to say 9 squared plus 12 squared. And the square root of all that, you're going to get 15. So then you're going to come back and say, all right, the unit vector is going to be 1 over 15 times 9 comma 12. And then that's going to be 9 over 15, comma, 12 over 15, and let's reduce that. 9 over 15 is going to be 3/5 And 12 over 15 is going to be 4/5. All right. Number 9. And we're going to leave this as a radical. This one doesn't work out so nice and neat. We're going to talk about the magnitude of P. And it's going to be the square root of 4 squared, which is 16, plus 1 squared, which is 1. So we're going to have the square root of 17. And so our unit vector, when we come back, is going to be 16 over the square root of 17. Not 16, sorry. I had a brain fart. It's going to be -4 over the square root of 17. And you're welcome to leave that radical on the bottom, over -1 over square root of 17. It's okay to leave it that way. Number 10, square root of 16 squared plus -8 all squared, so 8 squared is 64. That's going to end up giving you the square root of 320. And again, you're welcome to leave it square root of 320 if you wish. So the unit vector is going to be 16 over square root of 320, comma, -8 over the square root of 320. Number 11, we're not in component form, so we need to go to component form. So component form, we're going to say 6 minus 0, and then -1 minus -7, so that's a +6. So our component form is 6, 6. Now we find the magnitude of AB. That's going to be the square root of 6 squared plus 6 squared. And so that's going to give me the square root of 72. And so here we come back and we're going to have the unit vector is going to be 6 over the square root of 72, comma, 6 over the square root of 72. And yes, I know that'll reduce, but you don't have to. Okay, again, number 12 needs to go to component form. So the component form of PQ, 8 minus the -1, so that's going to be 9. And then -2 minus 4 is going to be -6. So there's your component form. And so let's go look at your magnitude for PQ. It's going to be the square root of 81 plus 36. So you're going to have the square root of 117. And then that's going to be 9 over the square root of 117. And then negative 6 over the square root of 117. Okay, now let's talk about standard unit vectors. The standard unit vector I and j are positioned along the x and y axis, and they're defined by I is going to be 1, 0, and j is going to be 0, 1. And you see that over here, we're going out 1 unit, and we're going up 1 unit. Any vector AB can be written in the form AI plus B times J. This is called a linear combination. So here's another vocabulary word that you need to add to your list. And you follow the steps to prove that this is equal to AI plus B times J. So you rewrite the two vectors. Let's say you have vector V, that's going to be equal to A comma 0 plus 0 comma B. And then factor out A and B. So in other words, I'm going to factor out A, and that's going to be 1 comma 0 plus, and I'm going to factor out B here, and so that's going to be 0 comma 1. And so here we've got 1 comma 0. Well, that's what we had up here, so that's going to replace this with I plus, same thing here, that's what we had for J, so that's going to become B times J. Right, so rewrite each vector in a linear combination. So again, this is A, this is B. So the linear combination is just going to be 2I plus 5B, or 5J, sorry. And the same is true for number 2. You're going to have negative 7I plus 3J. Now, number 3, you're not in component form, so first let's get to component form. So negative 5 minus a negative 9 is going to be positive 4. And then negative 6 minus 8 is negative 14. Oops, not parentheses. Goodness. Component form. And now from that, to go to your linear combination is going to be 4I minus 14J. And the same is true with number 4. First thing you need to do is go to component form. So negative 2 minus a negative 10 is positive 8. 5 minus 6, negative 1. And now go to your component form. So it's going to be 8I minus J. 1J or just J. Okay, now if U is a unit vector, then the terminal point of U lies on the unit circle. So notice how this is tying back into the unit circle. So notice again, here is I, and here is J again. And then AB is sitting somewhere inside here. That's going to be our unit circle. Therefore, U, in the component form of AB, can be written as, remember on that we always said it was cosine of the angle, comma sine of the angle. That's how we always wrote those, that first was cosine and the second was sine. And so when we write U, that A and B component form of A and B is really the same thing as having cosine theta, because A is in the place of cosine and B is in the place of sine. So we could really take U and write it in this form of cosine and sine, or the linear combination. We could break it down even further and say, well, really U is equal to cosine theta I plus sine theta J. Because every vector is the product of the magnitude and its corresponding unit vector, again, we can write some more. Notice what we have. We have these two things going on, which means we have the magnitude of V times the unit vector, which is going to be cosine theta comma sine. Or you can write it as magnitude of V cosine theta comma magnitude V sine theta. Or you can go even further and write this as the magnitude of V cosine theta I plus magnitude of V sine theta J. All right, so let's do some examples. In the first example, we need to find the component form of each vector given the magnitude and direction angle. So that's going to be where we have our, what we just wrote, where we did, let's see if we can't write our formula first before we jump into writing it. So we would have here where we have the magnitude of V cosine of theta, comma, magnitude of V sine theta. That's what we had. Oh, forgot my little vector notes. So let's plug this in. And so we know this is 8. So I'm going to plug in 8. Cosine 60, comma 8. Again, we were given that. That's where it's coming from. Sine 60. And then from our unit circle, so we're going to have to break out the unit circle. And in radians, this is going to be cosine of 60, which is going to be 1/2. Yes, we need to do this. No, it's not fair. Then we're going to have 80, and then sine of 60 is √3/2. And so half of 8 is going to be 4. And then that 2 can cancel into the 8, leaving 4. So that's going to be 4√3. All right. So let's do the next one. Same thing. So we're going to say W equals, and follow along the same formula. So we're going to say 20 cosine. Oh, darn it, I didn't put my little vector signs again. 20 cosine 225, comma 20 sine 225. And so we're going to have 20 cosine 225. So that's going to be down in the third quadrant. So it's going to be negative √2/2, comma 20 negative √2/2. So we can cancel with our 2's. So we're going to get negative 10√2, comma negative 10√2. Okay. So K equals 12 cosine 150, comma 12 sine 150. And again, all these values are coming from that unit circle. So 12 cosine of 150. Let's see, the reference angle for 150 is 30. And we're in the second quadrant, so it's going to be 12 times negative √3/2, comma 12 times positive 1/2. And so 2's will cancel. And so you're going to get negative 6√3, comma 6. All right. Finally, one you can type in your calculator. So A is going to be equal to 30 cosine 340, comma 30 sine 340. And put that in your calculators. And that should give you 28.19 and negative 10.26. is what I got. All right, now we're going to write each vector in trig form. And we are going to go from component form to do this. So we need to, 1, get our magnitude. And then 2, we will need to find our angle. And that's where we said theta equals inverse tangent of B over A. All right, so doing that, our magnitude of vector V is going to be the square root. I got 289. If y'all get something else, let me know. And that's going to be 17. And for theta, remember you get tangent of theta is going to be B over A, so it's going to be 8 over 15. And I got theta to be 28.07. And that's in the first quadrant, so that is the angle to keep. And so they want you to write this in your trig form. So remember, it is your magnitude, cosine of the angle, (17) sine 208, or 28.07.